Hi, everybody. This is going to be a hopefully short presentation about the postulates of the kinetic molecular theory, how air pressure is measured, and just basically definition of pressure and how air pressure is measured, and then how to interconvert among the various units of pressure. Now, I think you're going to be pretty familiar with all the postulates of the kinetic molecular theory. I'm sure you've heard them in previous science classes, so let's just kind of page through these. The gas particles are spaced really far apart in comparison to their own size. You guys know that gas particles are indeed matter. We established that earlier in the year. They do take up some space, they do have mass, but they are so small compared to the space between neighboring particles that we just consider the actual particle itself, the space that it takes up, we consider that to be negligible. Gas particles constantly move at rapid speeds in straight lines until a collision occurs, and as a result, you get random motion. They move. You know, we've talked this year already that the kinetic energy possessed by a particle is directly proportional to its rate of motion. So when the temperature goes up and they have more kinetic energy, they're moving faster. When the temperature goes down, they're moving slower. But whatever their speed, they move in a straight line until they run into one another or the walls of whatever container they're in. And there's no rhyme or reason to it. It's just very randomized motion of gas particles. They're just constantly moving. They do not sit still. Some other postulates or ideas that are part of the theory. There are no forces of attraction between the neighboring molecules of gas. We talked about the different types of forces of attraction. All particles, have dispersion forces. And depending on what type of molecule it is that is in the gas form, they might also have some weak dipole-dipole forces. But here's the thing, since the particles are spaced so far apart, those forces of attraction cannot act or, affect one another over that great distance. The particles have too much kinetic energy and too much space, and so they can't act on that attraction and pull together and stay together. So, kind of think of it this way, like, yes, I have magnets that are attracted to my refrigerator, but if I walk across my kitchen and hold the magnet up, it's not attracted to my refrigerator because of the distance between the magnet and the refrigerator. The forces of that magnet are weak enough that you need proximity. Same thing with the gas particles. They're moving so fast and they're so far apart that lack of proximity doesn't really allow their forces of attraction to kick in and have it affect, neighboring molecules. And then just the idea that the collisions, when they do bump into each other, they just bounce off of one another and go in separate directions without any loss of energy. Now, pressure is the force per unit area. If you want to think about this, for example, like when you are, when you're standing up, okay, the force that you feel is your body weight pushing down on your feet, okay? The area over which it's distributed is like whatever area of your feet are touching the floor. And then that creates the force distributed over the unit area creates the pressure. You're going to see in a minute one of the typical, pressure units is PSI, pounds per square inch. That would be your body weight measured in pounds. The area of your feet touching the floor in square inches, you get the PSI, the pounds per square inch that your body is, putting onto your feet where they're touching the floor. Now, if you, are standing on 2 feet and you pick 1 foot up, then the area that is touching the floor goes down, and as a result, the pressure goes up. Same force, okay? Kind of like remember this later when we're talking about properties of gases. Like if we change the area, surface area of the container, we might have exactly the same number of gas particles moving at the same speed, striking the walls, but if it's distributed over a smaller area, then the pressure goes up. And vice versa, like if, if you, for example, if you lay down, okay, you still weigh the same amount, right? When you lay down. So your force is the same, but now your body has a lot of area that's touching the floor. So if the area that's touching the floor increases, you're dividing by a bigger number, that's going to cause a pressure decrease. So both of these factors, can affect the pressure that's exerted by particles. How could the force change? Oh, hold on, I'm having trouble getting the pen. How could the force change? Well, the force would change. Oops. Oh gosh. Every once in a while I do that. Was on the eraser, not the pen. But no, what's going on? I don't know why I'm not going. There we go. Okay, back to it. But the force can change if you heat a gas and the particles are moving faster. They will hit the walls of the container harder, like that would go up, and then the pressure would go up. So we'll talk later about how like changing the size and the speed of the particles, the size of the container and the speed of the particles affects pressure. And so if you always just kind of come back to, this definition, and think about it, then that should hopefully, help you to understand how those effects, occur. So this is basically not how barometers look or work anymore. Evangelista Torricelli, who was an Italian scientist, made the first barometer that would look something kind of like this in the 1640s. So we're coming up on almost 400 years ago. But he was able in the 1640s to measure air pressure. And his original barometer looks something like this. It's a glass tube with mercury in it. Up here, there's nothing up there. It's a vacuum. How do you get nothing up there? Well, like if the tube, which is open in the bottom, like if you could go down in here, it's open. If you fill a tube the whole way to the very top with mercury or water, did you ever like fill a container in the bathtub when you're a kid, put your finger over it, flip it upside down in the water? Then when you flip this upside down, the the water level might drop a little bit, but when the water level drops, then there's nothing up here in this space because it had been filled with the mercury or the water. Two reasons for using mercury instead of water. Mercury doesn't give you many vapors in this area, so that's better than water. Water puts a lot of vapor in there, so then it's not really a vacuum. And also, mercury has a greater density, so the tube doesn't have to be, quite as long, when you're using mercury instead of water. I think I read somewhere that his first tube where he first used water was like 4 or 5 feet high. This one you can see the height. It says here, this is 76 centimeters right here. And they mean from like here to here is 76 centimeters. So how does it work? Well, the mercury that's in the tube, okay, that's got some weight over this unit of area. And so it's applying a pressure there. The air is applying pressure out here. And as long as the level of mercury is not changing, that means the pressure applied on the outside and the pressure applied on the inside are equal. So Torricelli observed the height of the mercury in his tube for many days. And if the air pressure increased, then, that caused the mercury to move up to a higher level. And maybe on a day when there was less air pressure, then the mercury would drop to a lower level because less pressure was needed in here, so less weight of the mercury. So he noticed that the mercury tube would, change its height depending on how much air pressure was, pushing on it, and that he could measure the air pressure by the height of the mercury tube. When the tube was 76 centimeters high, he noticed that that was typical or normal air pressure. So normal air pressure became 760 millimeters of mercury. Okay, it can go higher or lower than that, but this is typical normal air pressure. So these are different units for gas pressure. They're all equal to one another, so you can use them to do conversions. You can see here is what Torricelli established in the 1640s using his mercury column. In honor of him, a millimeter of mercury is also known as a torr in honor of Torricelli. Since it is normal atmospheric pressure, it is known as an ATM. It's equivalent in some other units like PSI. I'm going down here to the bottom, like we were talking about. Hold on. Let me go from the current slide. Okay, so his units that that he established are equal to this many pounds. Accidentally, this many pounds per square inch right here. Okay, thought I was on this, but it's not. This many pounds per square inch. Bars and millibars, you hear them using those on the weather. And these are the metric units. You guys remember pressure is force per unit area. And so if the force is in newtons instead of pounds and the area is in meters squared instead of square inches, then you get newtons per meter squared, okay, which is a Pascal. That's a Newton meter squared. This was a really big number, so they also tend to use kilopascals, just to make it a smaller, more easily managed number. So these are equivalent to one another and can be used to do some conversions. Like here, if you have 895 millimeters of mercury, how many ATMs is that? Just set up a factor label. You guys know how to do that. Top and bottom of the factor need to be equal. We know that to go from millimeters of mercury to ATM, that from our previous slide, it is 760 millimeters of mercury equal to 1 ATM. And, we know then that the millimeters of mercury will divide out as a label, and our answer will be an ATM. And you take 895, you divide by the 760. I'm rounding to 3 sig figs, and I'm getting 1.18. Here's another one to practice. Maybe practice this on a piece of paper, and I will go over how to do that one in a second. So if you start with the kilopascals, to go from kilopascals to torr, you need the top and bottom of the factor to be equivalent. Previous slide, we know 760 torr is the same as 101.325 kilopascal. So we will take 1.25, multiply by 760, divide by 101.325. The kilopascals divide out, and I got 9.38, and that one is torr. And here's one more you can try. You will need to get good at doing these conversions when we get into the next unit, in Unit 9 in gas laws. We often have to interconvert our pressure units so they can match up maybe on both sides of the equation. And so knowing these equivalencies, definitely something you want to write in your notes from this previous slide, what is equivalent to one another. And so knowing how to use them to do factor labels like this. So if you look at the previous slide, it's 1.013 bars equal to 760 millimeters mercury. And so once again, the bars would divide out when you multiply by 760 and you divide by 1.013, round to 3 sig figs. I got 563. And the millimeters of mercury is the unit because it did not divide out. So hopefully that helps you out with, identifying postulates of the kinetic molecular theory. There were 4 postulates on the first 2 slides. Then the definition of pressure and how changing force or area is going to affect your final answer of pressure. And then what are the different pressure units and how you interconvert among them. So hopefully that has been helpful for you. And so hopefully you can get some practice now with other things. And then, yeah, look, there's Mr. Cohen. That's kind of fun. So.